Hi everyone, in this talk I'm going to introduce our recent work on verifying the probabilistic conformance between cyber-physical systems. Conformance is a relationship between cyber-physical systems. It basically says that two CPS models are similar to each other, so the results from analyzing one model automatically transfer to the other. There are several places where conformance are useful. And the first case is in model simplification. As we know, when we want to analyze a complex system model, we typically make heuristic simplifications. And a key problem is whether the simplified model conforms to the original model or not. The second application is in system update. As we know, cyber-physical systems typically undergoes frequent control program updates. And sometimes we want to make sure that some key system function, some core functionalities of the system does not change between these updates. In other words, we want to make sure the system model before the update conform to the system after the update. The third application is in system testing. When we test a cyber-physical systems, we typically want to make sure that the system behavior in testing is similar to the system behavior in usage. In other words, the system model in testing conform to the system model in usage. To comprehensively solve the conformance problem that I've just discussed, in this work, what we want to do is we want to design a software tool that can verify the different kinds of conformance properties for different kinds of CPS applications. More specifically, I would like to develop a conformance verifier that can read two CPS models and a conformance specification of interest and automatically check whether the two models conform to each other or not. For this goal, we can use formal methods, but we need to answer the following three questions. First, how to model cyber-physical systems. Second, how to formally express conformance specifications. And third, how do we develop mathematically rigorous algorithms to verify the conformance? So when it comes to dynamically model cyber-physical systems, a key problem is that their dynamics are typically hybrid and probabilistic. Here is an example showing the hybrid execution or path of a cyber-physical system. The state space of a cyber-physical system is usually hybrid that contains several patches of continuous domains. At each time, the system state can either evolve randomly within a domain according to some physical law or jumping between the domains because of a transition in the cybercontroller. To capture the hybrid and probabilistic dynamics of cyber-physical system, here we used a model called probabilistic uncertain models. It is basically a stochastic hybrid system where the system parameters are randomly generated from some unknown random processes. The good thing about this model, probabilistic uncertain model, is that it is very general. It subsumes previously studied system models such as hybrid automata and continuous time Markov chains. Moving on, I'm going to introduce how do we formally express conformance specifications. First, I would like to emphasize that conformance specification is a meta specification that may contain infinitely many simple specifications. Here is an example. Suppose we care about the startup process of a powertrain system, and we have two system models, one detailed and one simplified. Because of the system noise, the startup process of a powertrain is typically random, and we want to check whether the probability distribution of startup is similar across these two models. More formally, this conformance in startup time can be expressed by like this. Specifically, we want to make sure that the probability to start up by the time t is almost equal for both models across all possible values of the time t. This specification contains infinitely many simple specifications depending on the specific value of the time. To formally capture meta specifications for conformance, here we use parameterized signal temporal logic formulas. As you may know, traditionally, the simple specifications for cyber-physical systems can typically be expressed by signal temporal logic formulas. And here we show that by parameterizing those STL formulas, we can express the general meta specifications for conformance here. Here is a quick introduction on signal temporal logic. It is a formal language with 4 syntactic rules. And using these 14 syntactic rules, we can express a wide range of simple specifications of interest. For example, whether the system will finally reach a goal state, or whether the system state is always safe across a time horizon. And by treating the parameters in the signal temporal logic formula as free variables, we can capture the probabilistic conformance of cyber-physical systems by quantifying those, by putting a universal quantification over those free variables. Specifically, the probabilistic conformance in startup time that I just introduced can be expressed using parameterized STL formulas like this. More generally, by generalizing this idea of parameterizing signal temporal logic formulas, we can define the conformance between CPS models. Specifically, our definition for conformance goes like this. Given a parameterized STL formula with parameter d, we want to make sure that the satisfaction probability of phi is almost equal across the 2 models for all the possible values of d. Here, the approximate equality is captured by a threshold c. I would like to emphasize that there might be multiple parameters of that formula, so we can represent it by a vector. Verifying this conformance between cyber-physical systems is very challenging by traditional method. This is because they can only handle unparameterized signal temporal logic. Therefore, if we use them to verify this meta specification for conformance, we need to run over all the possible values of the parameters, which are infinite. Therefore, they are not computationally feasible. And our main contribution is that we developed a new verification method that can actually handle those meta specifications for conformance. Specifically, we can handle an important class of conformance specifications that are captured by monotonically parameterized STL formulas. By monotonically parameterized, we mean that the satisfaction probability of that formula grows or decreases monotonically with the values of the parameters across 2 models. This property typically holds for most conformance properties of interest in application. And we developed a statistical verifier that can check whether 2 CPS models conform to each other with respect to the monotonically parameterized formulas or not by sampling from the 2 models. Since our verifier is statistical, it is possible that it will return a wrong answer, but our guarantee is that for any given parameter alpha that is greater than 0, which we call its significance level because it captures the error probability, the maximal tolerable error probability. For any given alpha greater than 0, the statistical verifier can smartly decide how many samples to take and guarantees that the returned result is correct with probability at least 1 minus alpha. The reason why we take a statistical method is that here we are handling complex probabilistic and hybrid dynamical systems and also complex conformance specifications. Therefore, statistical method is the only scalable choice. Also, there might be unknown noises in the system models, and the statistical approach unfortunately is tolerant to those unknowns. Also, our statistical verifier provides a probabilistic guarantees on the result, and this probabilistic guarantee is sufficient for most applicational uses. Now I'm going to introduce you how do we design such a statistical verifier. For simplicity, for now, let's assume that the parameters are scalars. What we first observe is that since the parameter is monotonically parameterized, we can define their change of satisfaction probability over the parameters by two functions, and actually we can prove that these two functions are two cumulative distribution functions. Because of this, actually we can convert the conformance requirement to a requirement on the L infinity norm between these two distribution functions. That is, the two systems conform to each other if and only if the two cumulative distribution functions are close to each other by a factor c. And we can check this by statistical inference, specifically hypothesis testing. Again, since we don't know these F1 and F2 two distributions explicitly, so therefore we need to approximate them by samples. Suppose I have n samples from the first distribution and m samples from the other distribution. Then I can draw histograms from those samples and using the empirical distribution represented by those histograms as approximations to the two distributions. This is the mathematical definition, this is the mathematical formulas that can generate those empirical distributions. From basic statistics, we know that the actual difference between the two distributions can be approximated by the distance between the two empirical distributions. And when we got infinitely many samples, this approximation will be perfect. However, in reality, we cannot draw infinitely many samples. Therefore, we need to have some finite sample analysis on the error bounds. For this goal, we'll first introduce a new variable called delta nm. It basically captures the difference, the estimation error, in using empirical distributions instead of the real distributions. Our key observation here is that the probability distribution of delta nm, rescaled by a factor that depends on the number of samples m and n, obeys the Kolmogorov-Smirnov distribution. And this distribution is independent of the form of the two unknown distributions f1 and f2. Therefore, by theorem 1, we know that actually we can provide a uniform bound on using empirical distributions to estimate the error for all possible forms of the real distributions. Based on this, we can also get the significance level if we make a statistical assertion based on the finite samples m and n. Specifically, this is given like this. Suppose I stop my algorithm when I have n samples from the first distribution and m samples from the other distribution, and this is the significance level I will get if I make a statistical assertion based on that finite sample sets. Moving on, if we want to achieve a desired significance level, what we need to do is just increasingly draw more and more samples until the significance level of my statistical assertion for those number of samples is smaller than the significance level I want. And these two theorems guarantees the correctness of the result of the algorithm. First, we can show that if the real difference between the two distributions is not exactly equal to the threshold C, then the algorithm will stop with probability 1. And also, whenever the algorithm stops, the return of the significance level will achieve alpha, which is the desired one. So by using these statistical inference techniques, we developed a statistical verifier or statistically verification algorithm that can verify the conformance between cyber-physical system models. Now I'm going to show you how can we use that algorithms to solve some of the important application problems for cyber-physical systems. The first case study is on the Toyota powertrain system. Specifically, this is a system that captures the dynamics of a car engine that is controlled by an embedded controller. For this model, for this system, the full dynamical model is highly nonlinear and very hard to analyze. Therefore, in practice, we typically approximate that nonlinear dynamics with polynomial dynamics by doing a Taylor expansion. And we are interested in whether this simplified model and the detailed model conform to each other in terms of analyzing the startup time. And the startup time specification, conformance in startup, can be captured by the formula like this. We perform a statistical verification on conformance for different values of the threshold C and confidence level. This confidence level is basically 1 minus the significance level. Surprisingly, we show that these two system models does not conform to each other. This is fairly surprising because it has long been believed that the simplified and detailed model of the powertrain conform to each other in many important specifications. Our second case study is on the lane keeping control of autonomous cars. Specifically, we are interested in a car that is controlled by a lane keeping controller to track a detected lane. To do this, traditionally, we use model predictive controllers. But recently, it is shown that we can also achieve this goal using neural network controllers. And here we are interested in whether the system under these two different kinds of controllers achieve the same tracking error or not. And formally, the conformance property in tracking error is captured by the formula below. We check the conformance between these two controllers for different values of the threshold C and the confidence level, and we show that for a relatively large threshold C, the two controllers approximately conform to each other. In our third case study, we care about a power system that is composed by a photovoltaic array, a generator of a photovoltaic array, and a user of a power grid that are connected together through a DC to DC boost converter and a voltage source converter. Again, the detailed model of this system is fairly complicated. And a heuristic method to simplify this model is by averaging the dynamics, namely filtering out high-frequency responses. For this case study, we are interested in whether the voltage deviation between the two models are similar. And this is formally captured by the formula of the following formula. Again, we check this formula for different values of the threshold and confidence. And surprisingly, we show that these two models do not conform to each other, meaning that when we analyze the voltage deviation, the high-frequency responses plays an important role. To summarize, in this work, we proposed a new method to verify the probabilistic conformance between separate physical systems, and using our new verification method, we can verify the conformance between separate physical system models in a wide range of CPS applications. All the codes for the case studies are available on our GitLab repository. If you have any question, please feel free to ask me.